uppercase I for product. Questions? Okay, now let us look at an example. I don't know if I should call this an example. This is actually a very important case. Now let us consider this. If RIT is given by e raised to minus lambda sub IT. So let us assume that they are subject to permanent failures and each has its own failure rate. Then the system reliability is equal. So we put that here and we get e raised to minus lambda 1 plus lambda 2 plus lambda 3 t. So basically what we notice here, that in a series system the overall failure rate adds. So we could say that that is equal to e raised to minus lambda sub st, where lambda sub s is equal to lambda 1 plus lambda 2 plus lambda 3. So the failure rates add in series systems. So more components you have, higher is your failure rate and lower is your reliability. So which is kind of a fundamental property. More complexity, lower reliability, because there are more things that can go bad. Now this is actually the principle that is used for calculating failure rate. There are some methods for calculating failure rates. So basically you find out, let's say you have a printer circuit board, you want to calculate the failure rate of a printer circuit board, you find out the failure rate of all the things on the board, including board itself, connections, all the capacitors, IC chips, and then add up the total failure rate, and that would be the failure rate of the whole thing as a system. So basically failure rates add. Okay, now let me ask you this question. There is the saying that a chain is as strong as its weakest link. How many of you have heard this? So a chain is as strong as its weakest link. How many of you agree with this? Okay, so why do you agree?
I mean, so it doesn't matter if the n chains are very strong. If there's one chain in between, one link in between them that's weak, so even if the rest are strong, if you pull them apart, that's going to break. So
that is correct. But any disagreements with that view or refinement?
Like I agree to a certain limit with this statement, because it depends, like when we think of the chain, like how many times that this will occur, like what is the probability of having that weak chains making an effect on the others?
Okay, so basically, if you have a case where you have a chain where everything else is strong, but you have one weak link, then that is a good approximation. That reliability of a chain is approximately equal to reliability of its weakest link. But actually that is an optimistic thing, because as you have said, the failure rates add. So even supposedly strong failure links, they have failure rate, and all those failure rates will add. So let's put in some numbers and let's see an example. Now let us say that R1, R2, R3, they are equal to 0.95, and we have R4 equal to 0.75, and we have a CD of serial configuration, then the overall reliability, and you can calculate as equal to 0.643. So basically, it is true that your reliability cannot be more than the reliability of the weakest link. And however, even though they were sort of close to 1, maybe we'll come back to this question. I said sort of close to 1. But when you multiply 3 of them, they are enough to drag this down even from here. Okay, now let us consider the other case. This is one extreme where all the units are essential. Now let us consider a case where you have a parallel configuration. Again, that is a way of and in parallel configuration, system is good. System works if at least one unit is good. Now, in terms of reliability block diagram, the situation is represented in this way. Here we have the units. Let's call it U1, U2, U3. This is the so-called parallel configuration. Basic idea is that now they are functionally identical. They do the same thing. That's the assumption. And so assumption is that they are functionally identical. And we need to calculate the reliability. Now, when you want to calculate the reliability, sometimes it is more convenient to approach the problem from the other end. That means consider unreliability. So now in this case, the reliability of the system is given by 1 minus probability all units are bad. Right? So it will work correctly, except for the case when all the units are bad. So even if there is a single good unit, then this will work correctly. Okay, so that is equal to 1 minus probability that the U1 is bad. And let me abbreviate, probability that U2 is bad multiplied by the probability that U3 is bad, right? And we can write that as 1 minus R1, 1 minus R2, 1 minus R3. Probability that unit 1 is bad is equal to 1 minus R1. And in general, we can generalize it this way. Let's write in general. In this case, the system reliability is given by 1 minus I equal to 1 to n, 1 minus R. Now, one convenient way I have found, that is to remember this expression, is to remember the fact that in a parallel configuration, the unreliabilities multiplied, you can write it this way, where RS bar is equal to complement of RS. Remember, reliability is a number between 0 to 1, so its complement is 1 minus that number. So in this case, the unreliabilities multiply. Now let us, now here, notice that a parallel configuration, it makes some assumptions. One of the assumptions is that you can correctly identify a good unit. So if this is the only one good unit, you are able to correctly identify this and switch your reliance to this unit. And another assumption is that when the unit that you are currently using, let's say this is running a process and it fails, you can correctly identify the failure and correctly switch to a good unit. So here it makes some somewhat idealistic assumptions. So this is parallel configuration is sort of an ideal situation, but it tells you this is the best you can do. And in an actual practice, if you have other limitations, like if you are not able to identify with total reliability that a certain unit is good, then the overall reliability would be somewhat less. Okay, now let's assume we have a system with parallel configuration, and we want to improve the reliability, and we are hoping to improve it by using redundancy. Then one question is how much redundancy you should use. Here's an example of parallel configuration. Here's an example. The problem: we need some system reliability, and let us assume that system reliability is specified as 1 minus some small number epsilon, where epsilon could be 0.05, it could be 0.01, could be smaller. So some small number here. Remember, when we are talking about high reliability, we are talking about reliabilities that are sort of close to 1, and the question is how close to 1. So the question is how many units are needed if all the identical units, they have, I'll call the reliability equal to Rm, and let's assume that Rm is less than Rs. If Rm is equal to or greater than Rs, then obviously you need just one, because a single unit will give you the reliability you're looking for. But here the question is how many of these somewhat less reliable units you need, and you put them together so in order to achieve higher reliability. So here's the solution. So 1 minus Rs is given by, as we have just calculated, 1 minus Rm raised to x, and this x is what we need to find how many of these. So, and remember that 1 minus Rs is epsilon, so this is epsilon equal to 1 minus Rm raised to x, and with a little mathematical rearrangement we get and here I could put some numbers in there.